All right, let's go over some questions from our Unit 1 exam. Start here. Okay, so first question, which of the following are important features of differentiating properties that can be used to detect, identify, and separate chemical substances? Okay, so we know if it is a differentiating characteristic, it needs to be an intensive property. That means it should not depend on the amount. And then here's one of them. And it cannot be extensive. Extensive means it depends on the amount. If the property value changes with the amount we have, it's not going to work. Okay, like for an example, mass or volume or something like that. And then the volumetric is does not make any sense here. And then it needs to be unique. That means it cannot be a system property such as temperature or pressure, because temperature and pressure is not unique to a given substance, because many different substances can be at the same temperature, like same room temperature. You can have water and then some other juice or some other liquid at the same temperature. So it doesn't work. And same thing goes with the gas. So it needs to be unique. And those are the two options. So 1 and 4 are correct, and that should be option A. Question 2. Which of the following phase changes involves absorption of energy by the system? Okay, so energy absorption occurs when we usually heat. Okay, so heating. And then if you think about these processes, condensing means going from gas to liquid. When this happens, potential energy decreases. Therefore, the system has to release energy. Therefore, option A is out. And option B, freezing. Freezing means liquid to solid. Again, when this happens, the potential energy should decrease, because in solid we have stronger attractive interactions, meaning lower potential energy compared to the liquid. Because energy decreases, system has to lose energy, therefore energy must be released. Therefore, freezing is out. Option C, depositing, that means gas to solid. Again, in gas, we have the weakest attractive interactions, meaning highest potential energy. In solid, we have much stronger attractive interactions, meaning lower potential energy. Therefore, you go from higher to lower potential energy, meaning energy has to release from the system. Okay, therefore, depositing is out. And melting is solid to liquid. Yeah, that works, because when you go from solid to liquid, the intermolecular forces or attractive interactions between the particles weakens. That means potential energy increases. Therefore, the system has to absorb energy. Therefore, correct option is option D. Okay, so I need some room. Maybe I'm going to really erase this so that I have room. Okay. Question 3. What is true about triple point of a substance? Triple point is a certain temperature and certain pressure where all three phases, solid, liquid, and gas, coexist. Okay, and then we have the same temperature and then at a certain pressure. Okay, so what is true? The average kinetic energy per particle is greatest in the gas phase. Now, here's the thing: average kinetic energy per particle and temperature are related to each other. Okay, so in other words, I mean, according to the particular model of matter, we define temperature. Temperature is a measure of the average kinetic energy. Okay, so because they are the same temperature, all three phases should have the same average kinetic energy. Therefore, this is out. The average potential energy per particle is greatest in the liquid phase. No, so in the we have the gas phase here as well. In the gas phase, we have the particles furthest apart from each other, meaning they have the weakest attractive interactions between the particles. Therefore, gas phase will have the highest potential energy, not the liquid phase. Therefore, B is out. Option C, the average kinetic energy per particle is smallest. No, average kinetic energy per particle depends on the temperature. Temperature is the same for all three phases. Therefore, they all have the same. All three phases should have the same average kinetic energy. For C is out. Option D must be the correct answer. The average potential energy per particle is smallest in the solid phase. Yeah, usually that is the case. In the solid, we have the particles closest to each other, meaning they're going to have the strongest attractive interactions. The stronger the attractive interactions, the lower the potential energy. Therefore, option D is correct. All right. Question 4. What would be the phases of substances A, B, and C at 760 millimeter mercury pressure and 87 degrees Celsius? Okay. Now 760, this is 700, so 760 must be somewhere around over here. And then 87 degrees Celsius means, because we have this in Kelvin, we need to add 273 to that, because Kelvin temperature is 273 plus the Celsius temperature, that is going to be 273 plus 87, and that is going to be 360. And it should be 360 Kelvin. So 360 Kelvin, and then 760 millimeter mercury must be around over here. Okay. And the question is, at this stage, what will be the phases of the three substances? Now we know we have wave pressure curves. Okay. Just to remind us about what wave pressure curves are. So wave pressure curve is the liquid gas boundary. Okay, this boundary. Okay, we know above this boundary we have the liquid phase, and below this boundary we have the gas phase. Here we have solid. Okay, so the same thing goes with the wave pressure curves. If you have wave pressure curve like this, okay, and then above the curve we have the liquid phase dominant, and then below the curve we have the gas phase. Now, keeping that in mind, with respect to C, we can see that this point, these conditions will be above the curve of C, meaning C must be in the liquid phase. So we need to select. So right now we can eliminate option B and option D because it says C in the gas phase. That is incorrect. And then we can see that with respect to both A and B, this condition is below the curves of A and B. Therefore, they should be in the gas phase, same phase. In the gas phase. And then option A is out because it says A is in the gas, B is liquid. That is out. A and B both are in the same phase, and therefore the correct answer must be option C. A is gas, B is gas, and C is liquid. All right, let me raise a few of things to make some room. Okay, which of the following options best ranks the volatility of the substances? Now, volatility means how easy it is for the liquid to go to the gas phase. Okay, weaker the attractive interactions between the particles, easier for them to break these attractive interactions and go into the gas phase. Because in the liquid, particles are closer to each other. You need they are strongly attracted to each other relatively. Therefore, we need to break these attractive interactions for these particles to go into the gas phase. Okay, so weaker substances with weaker attractive interactions between the particles will have a higher volatility because they go into the gas phase readily. And then the substances with strong attractive interactions will have a lower volatility because it's going to have a hard time breaking the attractive interactions between the particles in the liquid phase to go into the gas phase. Okay, now keeping that in mind, we say that C has the lowest vapor pressure at any given temperature. Just to remind us about what we're talking about here. Let's say that let's pick some a temperature around here. Okay. Now you see that the vapor pressure of C is around this much. The pressure of B is around this much, and the vapor pressure of A is around this much. So if you take any temperature like that, you see that C has the lowest vapor pressure and then A has the highest vapor pressure. Okay, that means C is the least volatile and then A is the most volatile substance out of these. So I'm going to say that we're going to start with C as the least volatile substance. Therefore, A and D are out. Okay, and then between B and C. C has the lowest volatility, but then A has to have the highest volatility because A has the weakest attractive interactions because it has the highest vapor pressure at any given temperature. Therefore, option B seems to be the correct answer. Let's see, so B is in the middle. I mean, B cannot be in an extreme. Okay, so that's another way of eliminating option C. Okay, so that is that. Let's go to question 6. Okay, I might need screenshot. Going to question 6. What is the normal boiling point of substance A? You are given the conversion between millimeter mercury and ATM. So we are told that 1 ATM is 760 millimeter mercury. Okay, so when we say normal, we talk about 1 ATM pressure, right? So that means we are around this value over here, 760. And then the question is, what will be the boiling temperature of substance A? So substance A meets that pressure line around here, and if we draw a line to the x-axis from there, you see that it is going to be between 330 and 340. And then the closest answer to that is option A. So I'm going to go with option A as the correct answer. Okay, so substance A normal boiling point must be around 330 something. Okay. All right, now questions. Is this question 7? Which of the following change in delta E versus temperature profiles best represents the change in the conditions of mixture of A, B, and C from 1 ATM 360 to 1 ATM 300 Kelvin? So what it tells us is we are cooling. Okay, and we at 1 ATM pressure. That means we are around this line, and then we're going to start at 360 Kelvin. 360 and 1 ATM. Let me pick a different color now. Okay, so 360 and 1 ATM should be over here. And then from there, we are going to go to 300 1 ATM. So 300 1 ATM is over here. So we are going from here to here. Okay, now we are cooling, first of all. Okay, that means delta E must be negative, because that's the first thing we need to appreciate. Okay, when you are cooling, that means system loses energy. By convention, delta E or change in energy must be less than 0. So in other words, negative. So and all of these are negative, so that is great. And also we are going from a higher temperature to a lower temperature when we are cooling. And when we read delta E diagrams, we always start at delta E 0. The reason is when delta E is 0, that means the change of energy is 0, meaning we haven't done anything to the system. That's where we start. Okay. In option A, you can see that we are starting at a lower temperature. Delta E 0 is a lower temperature. And then we're going to end up at a higher temperature. This cannot happen when we are cooling. Okay. Therefore, option A is out. And then when it comes to option B, we are starting at a higher temperature. Very good. And then when we cool, when temperature decreases, energy decreases. And then we have a phase transition here. This must be gas to liquid for substance B, which is over here. And then again, once all the B gas is converted to liquid gas, then again temperature decreases. So does the energy, until we reach the phase transition for A. Okay, and here we again have gas to liquid phase transition for A. That's why we have a vertical line. During those phase transitions, the temperature remains constant. This is TA, TB. Temperature remains constant, but energy is Energy goes down because we are decreasing the potential energy. Okay. Now, once all the A is converted to liquid again with temperature, energy decreases. This is what we have here. All right, so I think option B seems very reasonable. And option C is out because it only has one transition. There should be two transitions for B and A. Therefore, that is out. And then the option D is out because you cannot have these situations in these diagrams. The reason is, so this shows that the temperature is decreasing, but the energy is not changing. If temperature changes, energy has to change, because temperature changes means the kinetic energy changes. That means the total energy must change as well. Okay, for that reason, we can never have graphs like this for delta E versus temperature. Okay, so with that, let's move on to question 8. Okay, this. Okay. Which of the following statements is true about the change in potential energy and kinetic energy during the above process in question 7? Okay, so let's see. Now, question 7 is this process going from 360 to 300 at the same temperature. Now, if we are decreasing the temperature, the kinetic energy has to decrease. The average kinetic energy has to decrease. And also during the phase transitions, we are going from gas to liquid, meaning potential energy decreases as well. Let's see what we have here. Both average kinetic energy per particle and average potential energy per particle increase. Now, we notice that they decrease. So therefore, option A is out. Both average kinetic energy per particle and average potential energy per particle decrease. Yeah, that is reasonable. The average kinetic energy per particle decreases. That is true. But the average potential energy per particle increases. No, it doesn't increase actually. So when the gas become a liquid, the particles get closer to each other, meaning they're going to have stronger attractive interactions than before, and therefore the potential energy is decreasing. Therefore, that is out. And option D, the average kinetic energy per particle increases. Nope, that is out. When we are cooling, temperature decreases, so does the average kinetic energy per particle. All right, moving on to question 9. If you have pure samples of A, B, and C at the same temperature and pressure of 300 Kelvin and 300 millimeter mercury, which sample will have the lowest potential energy? Okay, so the potential energy is related to the strength of interactions. Okay, the stronger the attractive interactions, the lower the potential energy. They are asking about the lowest potential energy. Therefore, we are looking for the strongest attractive interactions. Okay, out of these three substances, A, B, and C, regardless of the conditions, C has the strongest attractive interactions. Okay, so C must have the lowest potential energy. But if let's look at the conditions here, we're talking about 300 Kelvin and 300 millimeter mercury. So that should be around here, right? Under these conditions, all of these three substances must be in the liquid phase. Okay, so it's a fair comparison now because they are not in different phases. Now, under these conditions, we know that C must have the strongest attractive interactions because it has the lowest vapor pressure at any given temperature, because it has stronger attractive interactions between the particles. Stronger the attractive interactions between the particles, the lower the potential energy. Okay, therefore the correct answer is option C. Question 10. If you have pure samples of A, B, and C at the same temperature and pressure of 340 Kelvin and 300 millimeter mercury, okay, so you know what, let's indicate that because it might be important. 340 Kelvin and 300 millimeter mercury. So under those conditions, 340 Kelvin is over here, and then 300 millimeter mercury is over here. So we are at this point. Which substance will have the lowest number of configurations? Okay, now here's the thing. Now under these conditions, okay, this point is above the curve of C, meaning C must be in the liquid phase. And then this point is below the curves of A and B, meaning A and B must be in the gas phase. Okay, gas phase have the highest number of configurations. And then the question is asking the lowest number of configurations. Okay, therefore the answer must be C, because C is in the liquid phase under those conditions. Okay, all right, so let's look at question 11. Let's see if I can take a screenshot. Okay. Question 11, distribution of particle speeds at a certain temperature T for substances M1, M2, M3, and M4 are shown to the right. Which of the following options best rank the molecular weight of these substances? They are the same temperature, okay? If that is the case, the particles with the highest mass will be moving the slowest, right? And the particles with the lowest mass should be moving the fastest. Okay, it's like a Tesla car versus Nikola 18-wheeler. If they have the same energy, the Tesla car will be moving faster because it is lighter. This is the same idea here. Now, lightest must be M4 because it is moving the fastest, and heaviest must be M1. So let's see. And it seems like that option is option C. All the others do not make any sense. Okay, so yeah, M1 cannot be the lightest. M1 is the heaviest. That's why it is moving the slowest. Because how do we know it's moving the slowest? This is the speed. You can see we have the lowest speed for M1 and the highest average speed for M4. All right, moving on. Question 12. Container A contains 10 grams of methane, and container B contains 10 grams of oxygen at 360 Kelvin. Assume ideal gas behavior. Which of the following statements are correct? Okay, so the question is asking about the pressure of container A and container B. Now, they are the same temperature and the same volume. And then only thing is we need to look at the number of particles. Okay, so we have methane, which is 16. Relative mass of methane is 16 with respect to hydrogen. And when it comes to oxygen, it is 32. The relative in AMU, or relative mass of oxygen is 32 with respect to hydrogen. So obviously, oxygen is heavier than methane. Okay, therefore it's going to have, if we have the 10 grams of oxygen and 10 grams of methane, you're going to have more of methane compared to oxygen. Because if you want to do it in a different way, the number of moles wise, 10 grams divided by 32 grams per mole for oxygen versus for methane 10 grams divided by 16 grams per mole. Okay, because you have a larger denominator in oxygen, you're going to have a smaller number of moles of oxygen or smaller number of particles of oxygen. All right, now here's the thing. Now, if this is the case, we know that we have more particles of CH4 in container A, meaning container A should have a higher pressure, because higher the number of particles, higher the pressure. Okay, let's see what we have here. Pressure A is greater because there are more particles in container. There you go, that is it. PA is greater because there are less particles in container. No, that is not correct. PB is greater because there are more particles in container B. No, PB is smaller because we have less particles in oxygen container. And PB is greater because, okay, this is a typo. I think we changed that to less here. Either way, PB is not greater. PB is smaller. That is out. So option A is the correct answer. All right, moving on to question 3. I'm sorry, question 13. Container A contains 10 grams of oxygen, but the volume is 300. And then we have container B, volume is greater, but we have 10 grams of methane there. And then what they're asking is, under these conditions, which of the following statements are true about the average speed of the particles? Now, here's the thing. Average speed is related to the average kinetic energy. And then average kinetic energy is related to the temperature, which is going to be the same for both containers, right? They are at 360 Kelvin. Okay. If that is the case, both CH4 particles and oxygen particles will have the same average kinetic energy. Okay. But because we have lighter particles in because CH4 particles are lighter than, because this is 16 versus 32, okay, CH4 particles must be moving faster to compensate for that lack of mass to have the same average kinetic energy. Okay, so the average speed per particle is the same in both containers. That is not right. More information is needed. No, we have enough information. The average speed per particle is greater in container A. No, in container A we have oxygen now, so that is out. Therefore, the correct answer is option D. The average speed per particle is greater in container B because you have lighter methane particles there. So that's the correct answer. All right. So let's go to question 14. The phase diagram of ammonia is shown to the right. Under which path would both kinetic and potential energy decrease? Okay. So we have options A to B. When you go from A to B, you are increasing temperature. Therefore, the kinetic energy increase. Okay. Therefore, that is out. And also, you can see that we are going from solid to liquid. Therefore, we are going from strong attractive interactions to weak attractive interactions. So potential energy increases as well. So that is out. And B to C is not going to change the temperature. Okay. Therefore, the temperature is not changing. Right. But when you go from B to C, that you're going from liquid to gas, the potential energy increases because the interactions or attractive interactions between the particles are weakened when you go from liquid to gas. Therefore, B to C is out. Okay, because both kinetic energy and potential energy has to decrease, not increase. Yeah, in B to C, only potential energy increases, and it is also increasing when you decrease it. All right, therefore, correct answer must be option 3. Let's say 3. We're going from C to D. Again, we are decreasing the temperature. The kinetic energy decreases, and also we are going from gas to solid. Now, for the potential energy is going from a higher value to a lower value. Therefore, it is decreasing. Because in gases, we have the weaker attractive interactions, higher potential energy. In solid, we have strong attractive interactions, therefore lower potential energy. Therefore, option 3 is absolutely correct. Therefore, the correct answer must be option B. All right, so let's go to question 15 and 16, the last 2 questions. Okay. Butanol is used as a lighter fluid. The molar mass of isopropanol is 60 grams per mole. I mean, that was a typo in this question. So the question, so we changed this to isopropanol. Okay, this doesn't matter. Let's say this doesn't matter. So we change this to isopropanol. So it's not butanol anymore. This should be isopropanol. Anyway, it should not matter with what the question is asking. Let's see. The molar mass of isopropanol is given 60 grams per mole. That's the information given to us. Which of the following is most likely the chemical formula of isopropanol? That's the question. So what we need to do is we need to determine which of these molecular formulas has a molar mass of 60 grams per mole. Okay, if you look at the first one, we have 4 carbons, that is 4 times 12 plus 10 times 1 plus 16. That is going to be 4 times 12 is 48. 48 plus 10 is 58. 58 plus 16 is 74. So this is out. And then C7H10O2 must be much greater than that. Therefore, that is out. Much greater than 74 even. And then C6H7N, 6 times 12 is 72. Therefore, that is not 60. Okay, we haven't even added 7 hydrogens and the nitrogen here. Therefore, option C is out. And the last option is 3 carbons, that is 3 times 12 plus 8 times 1 for 8 hydrogens plus 16. If you add this up, 3 times 12 is 36. 36 plus 8 is 44. 44 plus 16 is 60. Therefore, the correct answer must be option D. Okay. And then in a different version, you were asked to find the chemical formula that is consistent with 74 grams per mole, and that has to be C4H10O. So you see that the name of the substance doesn't matter here. So it is all about which formula is consistent with the given molar mass. If it is 60, it goes with C3H8O now, and if it was 74, it must be C4H10O. All right. Yeah, it depends on the version of the exam. Okay, so what is the mass? Last question, what is the mass of the sample that contains this many particles of butanol? And what is given to us is the number of particles, uppercase N. Okay, and then they're asking the mass. So the question is asking for the mass, right? There are only 2 equations we need. Number of moles is equal to number of particles divided by the Avogadro's number, and then the number of moles is equal to mass divided by the molar mass. So we are given the number of particles, so uppercase N. Therefore, this is given. We know the Avogadro's number, therefore we can find N. So let's do that really quickly. So this should be 2 times 10 to the power of 24 divided by the Avogadro's number, which is 6.022 times 10 to the power of 23 per mole. And when you do that, you're going to get something like 2 divided by 6 is 1/3. And then 10 to the power of 24 divided by 10 to the power of 23 is 10. So 10 divided by 3 mole of butanol, and whatever this sample is, right? And then what we need to do is, the question is asking for the mass, not the number of moles. So you need to use this equation now. From this equation, we see that we know the number of moles, we know the molar mass of butanol is given to us, so we can find M. So we can say that M is equal to number of moles times the molar mass. Number of moles is 10/3 moles. Multiply this by the molar mass of butanol, which is given to us as 74.1 grams per mole. Moles cancel out. And if we do this calculation, so you have 2 3s in 7, that is 6. And we have 14, you have 4 3s in 14, you have 2 left. And then in 21, you have decimal place here. In 21, we have 7 3s, therefore it should be 24.7. Multiplied by 10 is 247 grams. That should be your answer, and that seems to be our option B. All right, and those are the answers to the multiple choice questions together with the explanations. I hope this helped. I'll see you guys later.